All right, welcome back, folks. This is the second part of our series on quadratic simultaneous equations, or in other words, we are saying a combination of a linear and quadratic. We're interested in two x values, two y values. Let's have a look at these problems that we have here using the thinking that we got on the first part. Let's check. Solve graphically x squared minus 16 equal to 0. The moment they say graphically, we are bringing in variable y being equal to x squared minus 16. So everything will happen on our Cartesian plane. That's x and y. So somewhere below where we have our y equal to negative 16, it's a point of interest. And when we solve this particular equation, we are saying x squared is equal to 16. Therefore, our x will be equal to plus or minus 4. So on our graph where we have minus 4 and plus 4, those are points of interest again. So any curve which follows this particular fashion, that's y equal to x squared minus 16. So we have solved it both algebraically here where we got the solutions, as well as graphically. We are saying it's a parabola which cuts our x at points minus 4 and positive 4. Then moving on, we are being asked to solve another one again graphically. So one thing we know is when we make our equation y equal to x squared plus x minus 12, whatever we do on our Cartesian plane, y here and x, we are saying if we make x 0 on all paths, y will be minus 12. So our graph should pass through a point where we have minus 12. But then let's try and inspect if we can solve this algebraically to say, well, we'll try with factorization. Let's check. Are there two numbers such that you multiply them, they give you negative 12, you add them, they give you positive 1. That's where we'll try and bring in factorization to say we have something of this nature. And I'm sure those numbers are going to be 4 and 3 because minus 12 is negative. We check the middle part is positive, so negative goes to the smaller value. So our x is either positive 3 or negative 4. So what it means is on our curve where we have negative 4 and we have positive 3, those are also points of interest. And when I add these two, they give me negative 1. I divide it to give me negative 1. So somewhere where I have negative half, it's a point of symmetry of our curve. Then what's the last part? When I complete the square, I get the corresponding y coordinate of the turning point. What do I mean by completion of square? Here I'm going to say inside my brackets, I just divide this coefficient by 2. So I'll have x plus half, then I square it. Then the result that I get from squaring is a quarter. So I'll be subtracting it. It will give me minus 12 and a quarter. So there I've got minus 12. So just slightly below where I'll say minus 12 and a quarter. That point, it will correspond to our turning point of the curve. Let me pick a different color to just draw how the curve would look like. We turn here, we pass through that point. I'm sure my minus 3 is at the wrong, my positive 3. Let me try and adjust it so that there's a bit of symmetry on our curve. This point has to be positive 3. Then I can label my curve to say this is the curve y equal to x squared plus x minus 12. I've already sketched my curve, so I've solved it graphically. Then moving on, I'm having a problem here where I'm interested in making y the subject of formula. So making y subject of formula, in other words, I'll transpose everything to the right. So I want to remain with y only here. So I have to transpose 2x. So I end up having y equal to 9 minus 2x. Then the next part I'm required to do a substitution where I have y, let it be equal to x squared. So here is equal to x squared. So my next part is going to be x squared is equal to 9 minus 2x. Then what do I do from here? I'm going to put my equation in standard form. In other words, x squared plus 2x minus 9 equal to 0. With what I have there, I'll try and check, do I have factors of 9 such that when I add them, they give me positive 2? It looks like there's nothing, so I'll have to do completion of square. Then what do I do there? I'm just going to divide this part by 2. So it's x plus 1 all squared. So when I square 1, it gives me 1. But there is minus 9. Whatever value I get, I'll put it on the right side. So I proceed with x plus 1 squared. When I transpose here, I'll end up having 9 plus 1, which is 10. So x plus 1 is equal to root of 10. Therefore, the solutions are x equal to minus 1 plus or minus root 10. So those are the two values of x that I get after solving. Here I was just required to substitute. So if I'm to substitute, I'm sure this is what I'll get. And it's an equation that I've chosen to put in standard form as well as actually solving. Then simultaneous equations, where we've got a linear plus a quadratic, we are required to solve. So if we are solving, here they do not specify whether it's graphical or algebraically. Let me try algebraically, because here we are saying these two parts are equal. So I'm allowed to say x squared is equal to 4x minus 5. And when I put my equation in standard form, I'll transpose everything to the left side of the equal sign. So it will come like that. Then I'm trying to do by factorization. Say, do I have two numbers such that when I multiply them, they give me positive 5, and when I add them, they give me negative 4. Well, it looks like we do not have such factors. You multiply them, they give you positive 5. Now it looks like we do not have. So let me try and complete the square and check how far I'll go. With completion of square, I'm just going to divide this part by 2. So it ends up giving me x minus 2 squared plus 5. But when I square this, it gives me positive 4. So I'll put it there. Then next, I'll then transpose 5 there. So I have x minus 2 squared being equal to 4 minus 5. And when I do so, x minus 2 squared will be equal to negative 1. So x minus 2 will be equal to root of negative 1. So we can stop there that there are no real solutions because we can't find root of a negative value. Right, as we are moving, we are required to solve this problem below, where we have these two equations. As we can see, y is 2. So where I have got y, I'm allowed to put a 2. So I can come to say x squared plus 2x is equal to 2. And when I do my calculations in standard form, in other words, transposing all to the left, I'll end up having x squared plus 2x minus 2 equal to 0. Then completion of square again is x plus 1 all squared, because I'll divide this part by 2. There is minus 2, but when I square 1, I end up getting a 1. Then I'll transpose minus 2, so it'll be x plus 1 squared being equal to 3. So as I proceed with my calculation, I'll end up having x plus 1 equal to root of 3. So my x is equal to minus 1 plus or minus root 3. So I'll be having two values of x there. And I'm told my y is equal to 2. In essence, whatever I do, if I do my substitutions here, my y is going to be always equal to 2 because I'm given the value of y there. Right, moving on. I have another problem again that I want to solve. So solving algebraically, we are seeing that y is equal to y there. Therefore, these parts are also equal. So I'm allowed to say x squared is equal to minus x plus 2. Therefore, when I put it in standard form, in other words, I'll transpose everything to the left. That's plus x minus 2 equal to 0. So I'm trying to test, do I have two values? I multiply them, they give me minus 2. I add them, they give me positive 1. Looks like I have such. Then when I do so, because 2 is prime, its factors are only 2 and 1. Because I want the middle part to be positive, therefore the smaller one becomes negative, equal to 0. Therefore my x is either equal to positive 1 or negative 2. Once I have my x, it means I can find corresponding y values. When x is 1, there is x squared, so it means y will be equal to 1 as well. But when x is minus 2, when I square minus 2, it means y will be equal to 4 there. I think those are my solutions to that quadratic. Then let's try and make sense of the calculations we've been doing. How many solutions can a system of one linear and one quadratic equation have? Well, it depends on the nature of the equation formed. Well, we can have a 0 or 1 or 2. Let's have a look at the scenario which gives us 0 solutions, x, y there. The moment we have a curve which does not cross the x-axis, it means here we have 0 solutions. And I'll put it in red. The moment our curve, sorry, why am I not picking the red, right? The moment our curve touches the x-axis once, and here it will be 1 solution. Then in green, when our curve crosses the x at 2 points, then here we'll be having 2 distinct solutions. Right, moving to number 9, give a reason why some quadratic equations have no real solutions. Then the parabola does not touch or cross the x-axis. So when we draw our parabola or the quadratic curve, if it doesn't touch or cross the axis, it means there are no solutions. So sketch graphs to show a case with 2 solutions. So now if we have 2 solutions, we are saying our parabola or the quadratic curve, it crosses our x-axis at 2 points like that. Then we'll be having 2 solutions. Right. Moving on, one solution happens when our parabola simply touches the x-axis. It does not cross. So here we'll be having one repeated solution. Or because it's repeated, that's why I'm saying solutions, but it's just one distinct solution. No solutions, like we said it earlier. If there are no solutions, it means our parabola does not cross the x-axis at all. So let me try it in red to say a curve like this, you know that because there's a distance here, so there will be saying no real solution. I hope this meant a bit of some sense to you as we deal with quadratic curves or parabolas. I'm sure those are key concepts that we need to have in mind to say when we sketch our curve, which is the parabola, does it touch, does it cross, doesn't it touch? It tells us how many corresponding solutions we will draw from either the x and y. Thank you, folks.